Our next speaker is Ntavelis. He is a PhD student at the Computer Vision Lab of ETH Zurich and at the Swiss Center for Electronics and Microtechnology. He keeps himself busy with tasks revolving around generating and manipulating images. The title of his talk is Same but Different: Augmentation of Tiny Industrial Datasets Using Generative Adversarial Networks. Traditional GANs architectures require vast amounts of data that makes them prohibitive for industrial applications. Even will now present a method that enables that generation of images in the GAN setting, even for smaller data sets, and so brings such approaches a step closer to real-world applications. Evangelos? It's your turn.
Hello.
Hello.
Hello, I'm Evan, and today we're going to discuss about data. First of all, let's consider a problem. Industrial computer vision application, we want to detect faulty parts in a production line. The problem is that most of the parts that we have are healthy. This is not the problem per se, but we want to detect the problematic ones. And we don't have enough data of faulty parts. So what can we do? But let's not rush there yet. Okay, today we're gonna see what is the motivation behind this work, what kind of research tools and projects that are already out there we're going to utilize to create our own SSD-GAN, and the problem it tackles, and then we're going to discuss the next steps of this approach, how we can extend this to more application. Okay, let's talk about CSEM. I'm doing my PhD with CSEM, and CSEM is a research institute that is working very closely to the industry. So we have many industrial, real-world problems. In the many different focus areas, among them, there is data and AI and Industry 4.0. And in these fields, data is really important because you want to train and you want to create predictive models that you need to feed them with data in order to do what you want them to do. And data is valuable. Everyone agrees to this by now because everyone is trying to use AI, and AI is data hungry. But data is also abundant. Just imagine how much data you produce each day in comparison with 5 years ago. I upload more pictures, more text, I have more social interactions than that time before. So is that, okay, I have so much data now I can train any algorithm I want, is that correct? I'm not so sure because I don't think I can train my industrial image applications on your Instagram posts of your delicious avocado sandwich. So quality data is really important, but it's also laborious. 80% of the usual data science pipeline we spend it on cleaning and preparing data, and only 20% to the actual AI and deep learning part of the stack. So the question is, how do we use the recent approaches in machine learning and deep learning to generate new data, to help new quality data, to help us train better algorithms? Let's see some background information on this task. 6 years ago, a novel deep learning architecture was introduced. Instead of having the commonly used one network, we have two networks. One is the generator and the other one is the discriminator. You can think of them as two adversaries, two opponents competing against each other. The generator can be thought as a criminal, an art forger that's trying to create fake images of pieces of art, and the discriminator as the art critic that's trying to tell fakes apart from real pieces of art. So this game between the two makes them both better, and at the end we have a generator that is really good at generating fake samples. But don't take my word for it. Let's see some examples. all these faces that you see at this picture are fake, are imagined by a neural network. They're not real people. But image generation on itself, it's very valuable, but it's not what we want to do. We want to be able to control what is going out there. For instance, in this example, you have, I think, okay, the animation is not showing, but what you see here is you take an image as an input and you adjust its characteristics based on another exemplar image. And this can be done with other sources of information like text, audio, or just labels. And then you take one image and you translate it to something else. Another application of this is image manipulation. This is a recent work. It's currently under submission. And here we were able to give the user the control over an image to manipulate and change, to add objects, to remove things that an expert Photoshop user may have. But without any knowledge of these advanced tools, the user can edit images as they please. But what's the problem with all these approaches? They need a huge amount of data to train. So what we found very interesting is a recent work that was able to generate samples, images, using only one single image. They were able to produce astonishing results, but of course, this is limited. If you train on an image of birds or beautiful Swiss scenery, you cannot generate faces. But on the other hand, it shows the capabilities of working only on one image, and that one image, in fact, is composed of many smaller images, and we can utilize this information. And they were able to do amazing things with this model. They were able to edit images, to harmonize objects into images, to super resolve images, and all with the same trained model. To do this, they employed a cascade, a hierarchy of discriminator-generator pairs that started from a coarser scale, and at its level, by feeding the output of the previous level to the next, they were able to upscale and refine the output. In order to do so also, they tried to recreate the original image by fixing a point in the latent space, so it can have also a bit of supervision. But, natural images like these examples and industrial images are quite different. And this is why we introduced our method. But let's say at this natural image, for instance, if you look at every point of this image, there is information. If someone took from the exact same perspective an image 1 minute later, what you would see would be vastly different. This is a vivid live image. But when we go to industrial images, the setting is very calculated. We use special equipment to make sure that each and every photograph we take, for instance, of these parts is the same, and they are the same position, the same settings. And these pictures, even that they are from different objects, but they almost look identical. Or they? Because if you look closer, you can see many differences in the textures and the details. And these are the details we care about. This is why we introduced our same but different GAN. We employed, like SINGAN, a cascade, a hierarchy of generative discriminator pairs. The difference here is that instead of having one single image, we have a set of a cache of a small number, a handful of images. And the problem here is, because this is the case, we cannot just arbitrarily fix those images in the latent space, and we cannot use the same reconstruction loss as they did. For this reason, we employ same but different loss. We take our small dataset and our generated fake image, and we compare the fake to all the reals. Then we pick the two that are the most similar and the one that is further away. And what we're trying to do is we're trying to push the fake image as close to the similar ones and as far away from the different one, from the dissimilar. This creates, in our experience, a better representation and better results. And this is why we term this, and we coin this term same, but different. You can, as in SINGAN, you have this cascade of different scales, but instead of inputting the output of the previous scale, you can use your real image as input. This will create a difference, depending on the scale you input the image, of structural integrity and variability. Of course, if you do it on the lowest level, you lose a lot of information about the structure. But as you go on higher scales, you lose variability. So in order to create new images, because after a while you get the same structure but a different part in the end, you have to find the golden rule, the golden point of the trade-off between variability and structural integrity. In our experiments, that was mostly the 7th scale. But this is not the only experiment we ran. So here we just generated images. But then we took it one step further, and we tried to generate defects on images by ourselves. So we painted over some region, and the network was able to generate some defects in a healthy part. And this is very important for applications as the one we discussed earlier, when you want to detect difficult, problematic parts, and you don't have enough data. You can generate new data based on healthy parts. That was one way. Another way was, instead of have a user do it, just take a part from another image that maybe contains a defect and put it on a healthy one, and then pass this synthesis, this collage, from our model. We actually ran some quantitative experiments, and we found that in comparison to using no augmentation, or when you actually only cut and mix, you take the two different parts of different images and put them together, but not through our network, the results are worse. But when you take this approach and you put it through our SSD-GAN, then you get further better results. So, of course, in this experiment, actually, we used a dataset of 10 images. And if you are, we have a real-world problem and come to me with a dataset of 10 images, the first thing I will tell you as an engineer would be, please get some more. This will be the first step to increase the performance of your model. So for us as well, the next challenge is to take this approach and work on a larger dataset. All the examples we've seen before was from a model that was not specifically trained to generate defects. And because this is the most important target, our next step is to focus on defect generation or transfer of defects from a problematic part to a healthy one. And we think this is something that's feasible and will further improve the results we got here. To conclude, we've seen that in order to have a successful model, the quality of data is really important. Quality data is difficult to acquire them. And GANs that were able to produce and generate new samples were data hungry or were restricted in natural images. But what happens when you want to go to a different set of industrial images, which is quite peculiar? For this reason, we propose SSD-GAN to generate new industrial images only from a handful of samples. We've shown different approaches on how to utilize our model to generate new samples. One is just experiment a bit with different scales and produce new samples, or paint yourself some defects on healthy parts, or even cut and mix different parts to generate something new. Thank you. This is everything from me. I would be happy to answer any questions now and also by email.
Thank you, Evangelos. let me remind everyone that they can ask questions in the chat, and then I'll pass it over to the speaker. One of my questions would be: have you tried it on a different small data set approach?
No, in this work we have tried only with this data set, was because our problem was also quite particular. But I don't see any problem for this to run on another data set, given the fact that the data set is structured and follows the same rules as this one. Because in this one, every image was quite similar. And that's why we utilized a single image GAN, and we were able to get such good results out of it.
Right. So the requirement would be that the images are very related, right? The differences are minimal, are small.
Yes. We designed the loss function based on that premise. But I think if you change the loss function, it's very easy to adjust another approach among the data sets or problems.
I actually do have now a technical question regarding the loss from the participants. How is the SSD loss related to the triplet loss?
In the triplet loss, you have to mine the hard negatives. So this is very similar, but here we impose this sorting, and we take two positives. Instead, the triplet loss is between one positive and one negative. Here we take two positive. We found this to work better, and one negative. And the data set is, we don't have to do any elaborate mining because we have a small data set of 10 or 5 images. They are quite similar. The idea is very, very close.
So how would overfitting look in this context?
Well, overfitting, I think, would be that the network, the output of the network could be the only 5 or 10 images we're using and nothing else. But we found that at least in this case, that was not a problem. We were able to see, based on the scale, of course, a lot of variability on the finer details. The structure was as we wanted, so we didn't have any strains or out of distribution outputs in the structure. But yes, if we had failed and the model was only overfitted, then we wouldn't have any variability, and the network wouldn't take noise into consideration. And then it would be only input, upscaling, output, and having only 5 outputs.
Okay, thank you. One of the participants wants to know if you published the SSD-GAN. I'm not sure if now this is about the paper or about the model or the code, but you can tell us about both.
Sorry, I didn't.
If it's published, if the model is published, either
this one,
as a paper or on GitHub.
No, currently no.
So okay.
Any
plans?
This is the problem. This is a bit industrial, so we have to think about it. I'm always in favor of going to the open source direction, but this is something I can discuss with the other collaborators as well.
Okay. Thank you very much for joining us today, and I hope to see you again at the conference.
Thank you.
Bye-bye.
Goodbye.
Bye.